So welcome back. Today we are going to discuss about the Fourier transform. If you remember from our previous discussion on Fourier series, we say that if we have a periodic function, then the function can always be expressed in terms of linear combination of the sine and cosine waveforms. And then we can always represent f of x as this series a naught over 2 plus summation n from 1 to infinity an cosine of p n, okay, nx nx over p plus bn sine of nx over p so provided that this function is of period p, where a naught is given by 1 over p integral from, so this period 2p, so minus p to p f of x dx, and then an is given by 1 over p so there's pi here. So n pi over p, and then we have so n pi x over p, and then an will be given by 1 over p integral from minus p to p of f of x multiplied by cosine of n pi x over p dx, and bn is given by 1 over p integral from minus p to p of f of x sine of n pi x over p dx. So this is for values of n from 1, 2, 3, up to infinity. So this is the general Fourier series of a periodic function whose period is 2p. But in all cases, not all functions are periodic. For instance, the function sketched on this given graph from A to B isn't periodic. So when we have functions which are not periodic, we use what we call the Fourier transform to represent them, and the representation turns out to be integrals involving complex numbers, involving the tangents and involving the cosines and sines. So for non-periodic functions, f of x is not expressed as a linear combination of sine and cosines, but it is represented as an integral. So that will take us to the first theorem. So the Fourier integral theorem, or the Fourier integral representation of a function. So given that a function f of x satisfies two properties, one, that the function is piecewise continuous on every finite interval on its domain. And the second thing is that when you integrate the function from minus infinity to positive infinity, you get a non sorry for that. So given that a function f of x and its first derivative are piecewise continuous, so given that a function f of x is piecewise continuous in every finite interval on its domain, and when you carry out the integration from minus infinity to positive infinity, of this function, you get a value. Now that simply means that this integral exists. Then its Fourier integral representation is given by f of x equals to integral from 0 to infinity of a of omega multiplied by cosine of omega times x plus b of omega multiplied by sine of omega x. And then integration is with respect to x. where this coefficient A is given by 1 over pi integral from minus infinity to positive infinity of f of x multiplied by cosine of omega x dx, and B is given by 1 over pi integral from minus infinity to positive infinity of the function f of x multiplied by sine of omega x dx. So this is what we call the Fourier integral representation of a function f of x, which is not necessarily periodic on its domain. So instead of having the structure of the function being expressed in terms of the sine waves and cosine waves, the function is represented as an integral. So these problems on expressing a non-periodic function in terms of the Fourier integral representation sometimes may not be very easy due to the nature of the integrals we have to evaluate, which involves the infinite limits. So, but in more general form, we write the Fourier integral representation of a function f of x as so the function f of x is given by 1 over 2 pi integral from minus infinity to positive infinity of capital F of omega multiplied by e raised power I omega t, omega x integration is with respect to omega. This omega lies between minus infinity to positive infinity. Where this capital F of omega is given by the integral from minus infinity to positive infinity of f of x e raised power negative I omega x dx. And x here lies between minus infinity to positive infinity. So please note the way f of x is written. We have a factor 1 over 2 pi. Then the integration is from minus infinity to positive infinity. And then the integrand becomes a function of omega multiplied by the exponent of I omega x. And the integration is with respect to this number, omega. And then to define the function f of omega, you carry out integration from minus infinity to positive infinity. Then the function itself multiplied by e raised power negative I omega x dx. So both x and omega are real numbers, or simply they take values from minus infinity to positive infinity. So this is the main result here. That any given function f of x can always be written in terms of this integral, where this part f of omega can also be evaluated using this formula. So I want us to call this formula 1. I want us to call this one formula 2. So formula 1, which defines f of x, and then formula 2, which defines f of omega, which is involved in the expression of f of x. So this formula 1 and 2 together are called a Fourier transform pair. So one which defines f of x as an improper integral involving f of omega, and 2 which defines the value of f of omega, are collectively called a Fourier transform pair. And the formula 1 itself, or the formula 2, so formula 2 is what is called the Fourier transform of f of x. Which is sometimes written as if you remember what we did on Laplace transform. So to define the Laplace transform of a function f of x is simply L of f of x. So similarly, to define the Fourier transform of f of x, we write capital F to stand for Fourier transform, and then we put the function itself inside the curly brackets. So we say, so therefore, the Fourier transform of any given function f of x is given as the Fourier transform of f of x is given by f of omega, which is given by the integral from minus infinity to positive infinity of the function itself multiplied by e raised to power negative I omega x, then dx. So this is the main definition that actually we'll be using to compute the Fourier transforms of functions f of x. And you should be flexible enough to say that you can as well define the same thing if the function is given in terms of the variable t. So similarly, when you write the same formula is the Fourier transform of a function f of t is another function f of omega, which is the integral from minus infinity, positive infinity of f of t, e raised to power minus I omega t dt. You are seeing enough to see that you can always write the formula in terms of the independent variable t, or you can use x. So that doesn't really matter. The variables are dummy. So this is what, let's call this one alpha. So alpha is the definition of the Fourier transform of a function f of x, or you may say f of t, and give the formula as given below. So the formula has some resemblance to what we saw for the Laplace transform. The only variation is that if you remember, Laplace transform of f of x was given by L, was given in terms of S, and this is what we had. So f of s, meaning is a function of s. We had integral from 0 to infinity of f of x, e raised power. What the power of in the definition of Laplace transform? Negative st. But now remember, when I use x, I have negative sx dx. So you say if you change the lower limit in the Laplace transform to be negative infinity, and you replace S for omega I, then you get the same formula for Fourier transform. So later on, we'll see the way we can relate the Laplace transform and the Fourier transform. So, but this is just to appreciate the fact that what we have done before on Laplace transform, when it comes to the definition of the Fourier transform, there's some resemblance in terms of the integrals. The only variation is the power of E and the lower limit in the structure of the function, but other things remain the same. So having defined the Laplace transform of f of x, the formula given us so this formula given in this first case. So where now you have f of x and then 1 over 2 pi integral from minus infinity to positive infinity f of omega times e raised power I omega x d omega is what is called the inverse Fourier transform. So the formula f of x given by 1 over 2 pi integral from minus infinity to positive infinity of capital F of omega e raised power I omega x d omega, which is sometimes can be written as is the inverse Fourier transform of this function f of omega. So this is what we call the inverse Fourier transform for the function f of omega. So we can call this one beta. Let's call this formula beta. And as usual, note that remember you can always replace the argument x by t and vice versa. And the formula remains the same. But the difference between the Laplace transform and the Fourier transform is that the way we have written these formulas, alpha and beta, each of them has integral from negative infinity to positive infinity. And one formula has a factor 1 over 2 pi. The other formula doesn't have a factor out of the integration sign. But that is not the only way to represent the formulas. Some people have different ways of rewriting the same Fourier transform pair, such that one way is to put the factor 1 over 2 pi in formula alpha and then avoid it in beta or vice versa, the way you have written. Or another way, some people write both in formula alpha and beta, they put the factor 1 over square root of 2 root pi. So that should be very clear from the start, but we are going to take one root. But when you mix those different forms in different textbooks, they are still funny. So NB, there is no universal convention concerning the definition given for the Fourier transform pair. This is to say, some authors write one, the factor 1 over 2 pi in the formula given. So here this is alpha, and then we have this one, this alpha. So you see this formula alpha, there's no factor here. So we put in alpha instead of putting it in beta. Given in alpha instead of beta. So this is what I mean. So you write the pairs as f of x is given by integral from minus infinity to positive infinity of capital F of omega e raised power I omega x d omega, and you write f of omega to be 1 over 2 pi integral from minus infinity to positive infinity f of x e raised power negative I omega x dx. So this is how someone can define the Fourier transform pair. So which is slightly different from what we have given in formula alpha and beta. That the factor 1 over 2 pi is now written in the place of f of omega instead of it being in the expression of f of x. This is still acceptable. That's one way. Another way, we place a factor 1 over root 2 pi in both alpha and beta. So you write f of x is given by 1 over square root of 2 pi integral from minus infinity to positive infinity f of omega e raised power I omega x the omega, where you define f of omega as 1 over root 2 pi integral from minus infinity to positive infinity of f of x e raised power negative I omega x dx. So that is how another person can write the Fourier transform pair, where one formula defines the Fourier transform, another formula defines the inverse Fourier transform. But now, because of these different ways of defining the Fourier transform pair, we are going to pick one convention that we are going to use in our calculation so that we avoid confusion. But that's just to make you aware that when you meet a different textbook with different definition of the formulas for Fourier transform pair, these other two versions are still okay. But we want us to stick to one definition for the Fourier transform and its corresponding Fourier inverse transform so that we have uniform computations in our calculations. So to avoid confusion or mix-up, so argument that we are going to make here. To avoid mix-up, we shall stick to the definition given in alpha and beta to define the Fourier transform pair. Here's what I mean. That when we ask you to compute the Fourier transform of a function f of x, then you are going to use the formula, the Fourier transform of f of x, say f of t, because sometimes the function can be given in terms of either x or t, is given by Fourier transform of f of x, which will be a function of omega, would be given by the integral from minus infinity to positive infinity. Take the function f of x multiplied by negative or if you write, or if your function is in terms of time, so the Fourier transform of f of t still is a function of omega, So it will be the integral from minus infinity to positive infinity, f of t e raised to power negative I omega t, then dt. So this is the definition you are going to use in the computation of the Fourier transform. And then we use this to define the inverse Fourier transform. The inverse Fourier transform of f of omega is going to be the inverse of f of omega. So will be a function. If you use the first case f of x, then you'll get 1 over 2 pi integral from minus infinity to positive infinity of f of omega e raised power I omega x d omega, or if you are dealing with a function involving time, so we have 1 over 2 pi from minus infinity to positive infinity f of omega e raised power I omega t d omega. So that's the definition that you are going to apply. So whereby the coefficient 1 over 2 pi is placed in the formula for finding the inverse. But the formula for finding the transform itself has no factor outside the integration sign to make us actually solve the problems as much as following the exercises we are doing on the Laplace transform. So small break and then we come to the examples.